All right, so we paused on Unit 2 for a little bit to learn the unit circle. I'm going to continue to drill you on that as we go. We might pause in the middle of the second half of Unit 2 also to go back and kind of extend that a little bit so we're really ready for Unit 3 when we get there. But jumping back into Unit 2, this is going on page 66 when we're done. And we are going to review, most of today is a review of logs. We do them in Algebra 2. You also do them in Algebra 3, so some of y'all have had them for a couple years. But here's our first important concept that's not necessarily directly related to logs. Every operation has exactly one inverse, how you undo it, right? This is what we use to solve equations. So if my operation is addition, how do we undo addition? Subtraction. So the inverse operation is subtraction. I don't know how often the word inverse has been used with you for that. We usually say the opposite. You know, if it's addition, you do subtraction. You just kind of know that they go together. But those are inverse operations of each other. What's the inverse of multiplication? Division. Good. All right. What about cubing? Cube root. Very good. And then what about, and I love this big word here, exponentiation, which just means it's an exponential. I have a variable in the exponent and I need to get it out. How do I undo that? Negative. With a log. Thank you very much. That's how we undo it. Okay. So that's why we are reviewing logs today. This goes on to say recently we learned, well, recently we reviewed about exponential functions and their properties. We'd like to solve them, and we need the inverse operations, and we need to at least use them some of the time, and we may need to use logs. We don't always have to use logs, but sometimes we do, so that's why we need to understand it. So our big idea here, just as we can write rational numbers in decimal form, so 0.5 equals 1/2. They have the exact same value, they just look different, right? We can also write equations in exponential or logarithmic form. Okay, put out the whole logarithmic, but from now on, I'm probably just going to do log because it's easier. These forms create equivalent statements that represent the same claim. We are not changing the problem when we convert back and forth. We are simply rewriting it. It's a different way to write it, and depending on the exact situation, one might be better than the other for whatever it is you're trying to do with it. Okay? So here's exponential form. We've got log base b to the, I'm saying log, there's no log there, I'm sorry. This is b to the a power equals c. The base is b, the base of the exponential. Then we have log base b of c equals a. Those two represent, they're both true statements, and they're just different ways to relate a, b, and c together. But notice that the base of the exponential and the base of the log are exactly the same. So our notes are that the bases are the same. Okay, and then we're going to watch a little 3-minute video that kind of explains to us why logs are important to us. His speech pattern is a little much sometimes, but it's a good short video to explain things to you.
How does the difference between 0.00000000398 and 0.00000000398 cause one to have red eyes after swimming? To answer this, we first need a way of dealing with rather small numbers, or in some cases extremely large numbers. This leads us to the concept of logarithms. Well, what are logarithms? Let's take the base number b and raise it to a power p, like 2 to the third power, and have it equal a number n. We get an exponential equation, b raised to the p power equals n. In our example, that'd be 2 raised to the third power equals 8. The exponent p is said to be the logarithm of the number n. Most of the time, this will be written log base b of the number equals p to the power. This is starting to sound a bit confusing with all the variables. So let's show this with an example. What is the value of log base 10 of 10,000? The same question could be asked using exponents. 10 raised to what power is 10,000? Well, 10 to the fourth is 10,000. So log base 10 of 10,000 must equal 4. This example can also be completed very simply on a scientific calculator. Log base 10 is used so frequently in the sciences that it has the honor of having its own button on most calculators. If the calculator will figure out logs for me, why study them? Just a quick reminder, the log button only computes logarithms of base 10. What if you want to go into computer science and need to understand base 2? So what is log base 2 of 64? In other words, 2 raised to what power is 64? Well, use your fingers. 2, 4, 8, 16, 32, 64. So log base 2 of 64 must equal 6. So what does this have to do with my eyes turning red in some swimming pools and not others? Well, it leads us into an interesting use of logarithms in chemistry, finding the pH of water samples. pH tells us how acidic or basic a sample is and can be calculated with the formula pH equals negative log base 10 of the hydrogen ion concentration, or H+. We can find the pH of water samples with hydrogen ion concentration of 0.000000000398 and 0.000000000398 quickly on a calculator. Punch negative log of each of those numbers, and you'll see the pHs are 7.4 and 8.4. Since the tears in our eyes have a pH of about 7.4, the H+ concentration of 0.70398 will feel nice on your eyes, but the pH of 8.4 will make you feel itchy and red. It's easy to remember logarithms. Log base b of some number n equals p by repeating the base raised to what power equals the number. The base raised to what power equals the number. The base raised to what power equals the number. So now we know logarithms are very powerful when dealing with extremely small or large numbers. Logarithms can even be used instead of eye drops after swimming.
Okay. So does that make sense? Really big numbers, really small numbers, it just makes it easier to deal with, easier to graph, easier to understand, all that good kind of stuff. So you'll use them in math, you'll use them in your sciences, okay? And I'm gonna see if I can turn this off so that if I get any other messages, there we go. All right, so back over here. He made reference to the common log, right? And that is when it is log base 10. So this says if the base of a log expression is 10, it is called the common logarithm and is written without the base. Sometimes. I'll clarify on that in just a second. For example, if I just have log of 3, it's understood that you have a base of 10. So log 3 is equal to log base 10 of 3. Before AP Pre-Cal, what I would say at this point would be you are never ever going to write the actual 10 there, and you will never see it that way unless we're explaining it like this. But then, lo and behold, a lot of the College Board material actually has the 10 there. And I don't know if they're trying to be nice and make it easier, but to me it makes it confusing because logs aren't new for you at this point and nobody teaches it that way. So I want to throw that out there that, you know, whether you put it there or not, it's kind of like having the exponent of 1 on x. It's not wrong if you put the 1 there, you just usually don't see it and you don't need it, right? And it would be highly unlikely you would see it on a test or whatever. But the base of 10 actually being there, that is something you could see on the College Board materials. So just throwing that out there. I guess there's not really like a rule that you don't do that. So I just find it strange that they do that, but whatever. Okay, so right now we're going to convert. We're not solving for anything. We're just converting, right? Writing it back and forth. So this is an exponential. The base is 3. So this becomes log base 3 of 9. You go around the equal sign equals 2. So you just make a little circle around the equal sign. It's that easy. Okay, we good on that? So then the base of this one is 10. So we can write log base 10. We'll write it this time. And then we go around, so that's of y equals x. Okay. We all good with how that works? Any questions? All right, so then this would be log base what? R of w equals t. Good. All right, then this would be log base what? E, of what? Y equals 3x. It just goes around the other way, right? This is the base, and then we would go around the equal sign the other way. All right, so let's go back to B here, because as I just said, we can write it that way, and you might see it from College Board like that, but you could also write it this way. Log of y equals x. Both of those are 100% acceptable. What we wrote on D, there's a different way too, but it's not the different way, it's the right way, because what we have there, right there, not acceptable, not okay. It is what is happening, like we didn't do anything wrong, we just have to change how it's written. So if I have log base E of, let's say, A, okay? Log base E is a totally different log, and it's a special one. That is the natural log. So that is a lowercase ln. That is the natural log of A. I can tell you with confidence that you would never actually see it written this way unless we're explaining it, and it would never be okay for you to write it that way, okay? And that is, again, a lowercase l. Think of it as log natural for natural log, because I see capital I's a lot of times. It's not the word in, okay? It's natural log. And so what this really becomes, instead of log base E, this is the natural log of y equals 3x. This is the right way to write that. And when you see natural log, then you know the base is E. Kind of goes both ways. Any questions about that? Now, the logs, the LOGs, we'll use both of these in pre-cal. In sciences, you could use both of them. When you get into calculus, you're really just using natural logs. And then, but again, that doesn't mean you're done with the logs, because if you get in another math or another science, depending on what you're doing, just depends on what the applications are, okay? Any questions at this point? All right, good deal. Then let's look at this. Now we're gonna go the other way. So now I have them in logs, we're gonna write them in exponential form. The base of the log is 7, so the base of the exponential is 7. So this becomes 7 to the second power, we go around the equal sign again, equals x. And that's 49, but we're not really solving, we're just rewriting, so we'll just leave it. The base of the log here is 3, so I get a 3, go around the equal sign, that'd be 3 to the x power equals y. Any questions about where anything's coming from? All righty. Then what's the base here? 10. 10 to what power? 2 equals y. Good. What's the base here? E to the what power? 4 equals c. Very good. Any questions about that at all? All right, flip it over. Okay, so sometimes we can evaluate log expressions without the use of a calculator by equivalent exponential form. Sometimes we need the calculator, sometimes we don't. So here's some where we don't, and we're not using a calculator on this. In order to evaluate that, I think the best way to do this is to always make it into an equation. So just make this equal to x. Okay. Then we're going to rewrite it as an exponential. The base is 2. I would take that to the x power, and that equals 8. Okay. Then we're going to get common bases, meaning I have a 2 over here. 2 to the x equals 2 to some power. What power do I have to take 2 to get 8? 3. Okay, so do you see how I have common bases there? And that just means that x equals 3. Everybody okay with that? Right, so now we are going to put this equal to x. This would be 5 to the x power equals 25. So 5 to the x would equal 5 to what? 2. So that means x equals 2. Now, you don't always have to write this second step, but I did that because sometimes you are asked for that. Okay, so let me go back to what I was saying before the phone rang. Sometimes you'll be asked to write them this way, or sometimes you might need to do other things. So I want you to understand what it means to get common bases. But when we get here, if we make this equal to x, so then I get 2 to the x equals 32, I don't have to actually write the other part down every time. What would x equal here? 5. Very good. Then here, let's set this equal to x. What's my base? 10. So 10 to the x equals 100. So x equals 2. Okay. We good? So I was going to have you do these next ones on your own also, but in the interest of time, because it took us forever at the door and then I got interrupted, let's just do these together. Make this equal to x. So 16 to the x equals 4. What would x have to be? 1/2. Very good, because I would have to take the square root. Okay, we good on that? All righty, so then I'm going to set this equal to x. So now I have 3 to the x equals 1. What would x have to be? 0. Very good. Anything to the 0 power is 1. All right. Equals x. What's the base here? 10. So 10 to the x equals 10. So what does x equal? 1. Very good. Equals x. So 6 to the x equals 1/36. So what does x equal? -2. Very good. You need to square it to get the 36, and then the negative gives you the reciprocal. Okay, everybody good so far? All right, so in the video, he said that the calculators have their very own log button for the common log, like it was just impossible to do log base 2 of 7. Even though, and he was referring to this, well, the older version of these calculators, but even in these, there's a menu where you can do something like log base 2 of 7. You just got to find it. We are using Desmos, but I do want to give you a little heads up that for college courses, you may not be able to use Desmos. It's not that they are anti-Desmos. I mean, they may be. I don't know why anybody is, because it does the same thing. It just does it easier and better, but whatever. But it has to do with the systems that they have. So the San Jack math department policy is these calculators, or I think there's one other thing, but I can tell you at least for sure for college algebra, I'm going to go back and read the syllabus again. You cannot use, I mean, you can use Desmos, but you just can't use it on a test. And I think it's because of their lockdown browsers and things like that. Now, I think that's true at a lot of college campuses. Those things might be changing over the years as people just get a little bit less scared of Desmos and can make it work with their systems. The problem is, though, y'all might have never used these. I had to spend quite a bit of time last semester teaching my college algebra kids how to use this calculator because you aren't familiar with it. I mean, it's not that big of a deal, but it is very different than Desmos, and Desmos is a lot easier. So I'm going to tell you, even though instead of y'all getting your computers out to do this on Desmos, I'm going to tell you what to do, just because, again, I know you can type things in. And I'm just going to give you the answers, so then you can go back at some point and make sure you can actually get these numbers so you know you're doing it right. So if I want the log of 9 in Desmos, I literally type log 9, and there's your answer. And that would give you 0.95424. And log of 6125 would give you 3.78710. If you have a base other than 10, you have to get a subscript. So in Desmos, you use the underscore. Y'all know where the underscore is? It's below the dash. You hit shift on the dash so you get the underscore. So if you type log and then do the underscore, it'll drop it down there for you. You can type in your number and then you can arrow to the right and it pops it back up. Okay. And if you forget or get confused, let me know. Or you can Google it. Google is your friend. You should get 3.32192 and 2.52081. Okay. So those are just some numbers so that you know what it should be. You can make sure that that's what you're getting. Okay. Everybody good so far? Okay. Now here comes another example of why we care and the new part of all of this for you. And I know this is a lot of words, but they're important, so I'm going to read most of these to you. One useful purpose for logarithms is when dealing with exponential data. Exponential data can be very challenging to display graphically because the values may start out very small, but they grow very quickly. It's difficult to create a display that effectively shows the smaller values along with the extremely large values together. So the population of English Americans in the current United States since 1620 has grown exponentially. The estimated population is shown below. So, and it says here, look, where t equals 0 represents 1620. You are most likely never going to use the actual year for the input, even though some of y'all still trying to do that. If you got years, it's probably going to tell you t equals 0 or t equals 1 represents a specific year, and then you got to use your brain. Okay. But if you look early on at these first few years, these first 4 don't even look like they're any different at all, right? Because these numbers were very small and then it grew very quickly. Your y-axis counts by millions, 1 million, 2 million, 3 million. So that still could be a lot, but you know, I mean, it took a while and then things just take off. So that's what all it says, blah, blah, blah. I think I pretty much said that. Okay, then the graph on the right uses a logarithmic scale. This is where things change for you. Our x-axis still spaced out like we've been doing our whole lives of graphing, but the y-axis is not. This is 10 to the first, 10 to the second, 10 to the third. So that means this is 10, 100, 1,000, 10,000, 100,000. Do you see how it's not spaced evenly, right? And so this is called, that axis is logarithmically scaled. I know it's a lot of big words. This is what's called a semi-log plot, semi meaning half. So one of the axes is logarithmically scaled, but not the other one. You could have a graph, well, we won't, but it exists that you could have the x and y both logarithmically, but that's not what this is. This is good old, from the good old days, how we scale things and then logarithmically scaled. Now, and it's the same data. So now look at the first few. Do you see how you can tell there really is a big difference between them, right? And then things then those really are kind of evens out, but that's a huge difference. You just can't see it when it is graphed like that, okay? Does that make sense to you? You see the difference there. Okay, we're not done talking about this. Grab the other sheet of paper because it has the same graphs at the top, and then we're going to continue. Page 66 here. All right, so again, same graphs. We're looking at this, right? Okay, so then the population for 1840, 1860, 1880 is given below. So in 1840, the population went to 17 million. This only goes to 7 million. 17 would have to be way up there. Then it goes to 31. And if I actually made that graph where I could fit it on my paper, it would squish these points down even more to more look like these, right? So it would be, the more data I get, the less and less any of this down here makes sense. But let's talk about how we would take that data and put it on here, okay? So we've got the actual population, 17 million, and so we're going to take the log of the population, okay? So we want the log of 17,069,453. And again, if you needed that, you can just type that in on your little keyboard and it'll spit this number out for you. 7.2322. Oh my God. Okay, so everybody understand? I just typed it in and got that number, right? If I rewrite this, listen, I'm going to rewrite this as an exponential. What's the base of that log? 10. So that means that 10 to the 7.2322 power equals 17,069,453. Because I still have to graph the right data. Like this isn't the population. This is what equals 17 million. You with me on that? So the log of the population here, we got 7.2322, but the actual population in logarithmic form is 10 to the 7.2322 power. So if I was to type this in the calculator, I'm going to get 17 million. It's just a different way to represent that number. You with me on that? So if the other numbers then, let me just give that to you. Oh, I put them down on my freaking desk with the freaking phone. Okay. This will be the day they come on with 1,000 announcements and I can't finish. We get 7.4975. So that means that's 10 to the 7.4975 power and 7.7006 and then 10 to the 7.7006 power. So I'm just giving those to you. You would be capable of figuring them out, but then we're going to plot them. Okay. I'll put this back up here in just a second after we plot. So if you look back up at this graph, again, we have 10 to the first, 10 to the second, all the way to 10 to the 7th. So instead of having to go way up off my graph, the first thing I need to plot is 10 to the 7.2322. So at 220, I'm just a little bit more than 10 to the 7th, And then at 240, I'm a little bit more than that. And 260, I'm a little bit more than that. And it just kind of continues the trend. But that's more useful. That's a better graph. It makes more sense for what was actually happening. And so again, depending on the kind of data you have, what you're looking for, logarithmically scaled graphs could be helpful. Okay. Now, we have to understand the semi-log plots, but the good news is we don't have to be fully immersed in them. You're not going to have to do this part again on your own, and you're not going to have to plot them. We did this so you could kind of understand what the heck was even happening and why we care, right? But what you do have to recognize, oh, I knew it. All right, do you see this grid? Listen, this is very important. This grid looks way different than any grid you've seen to graph on, right? You're used to squares, sometimes rectangles if things are stretched, but nothing that looks like that. But the other one, the graphs that we were looking at just didn't have all these lines on it. This is 10 to the first, this is 10 to the second, this is 10 to the third. This one, see how we start at 1? We don't even start at 0. This is 10 to the 0. That's what makes it logarithmically scaled. When you count these lines, look, this is 1, 2, 3, 4, all the way to 10. And the closer you get to 10, the closer the lines get together, right? Because that's just how the numbers work. And if you understand how this graph works, if you've actually seen one, it's really not that big of a deal what you are expected to fully understand. Once I get to 10, then it's 10, 20, 30, 40, all the way to 100. Then it's 100, 200, 300, all the way to 1,000. Then it's 1,000, 2,000, and so forth, okay? It may seem weird, but remember, you don't have to have a super hard grasp on that. You need to understand how to plot the points and how to recognize the graph. And so here, if I want to plot this point 120, this is still XY. Your x-axis, good old x-axis that we all get. This is 1, this is 10, so that makes this 20. That's A. Okay. Does it make sense? Even if it makes sense and doesn't make sense all at the same time, that's okay right now. All right, so then 2, 300, I go to 2. This is 100, so then 200, 300 right there. Three, 2. This is 3. This is 1. That is 2. 3, we start at 1. That is 2. You don't start at 0. 4, 15. Here's 4. This is 10. This is 20, so 15 is halfway. That's D. And then 5, 350. So 5, this is 100, 200, 350 right there. Woo, we did it. Yay. Go back and watch this again or ask me questions tomorrow if you need to. And be faster at the door.